the Seagrass video is going to be loud. Okay. So today we are going to be doing 6.6, which is going to be square root and cube root functions. So the main idea here is that with a square root function, the domain is always going to be restricted because, as you can see, it always is almost like a ray in geometry where one endpoint is there and then the other one is going off to infinity in whatever direction it goes off in. And a square root function is actually an incomplete version of the inverse of a quadratic function. You all see how it looks like a quadratic, but it's half of it and it's turned on its side, okay? And that's because the square root of x squared, they are inverses of each other. And then we have a cube root function, which is the third root of something, and that is actually the inverse of a cubic function, as you can see. And the cool thing about a cube root function is that its domain and range are always all real numbers. So we don't have to worry about domain and range. Now, domain and range of a square root is a little bit more complex. Okay. So first thing we're going to do is we're going to just talk about how we graph the parent function of these two using a table. Now we picked these numbers very strategically and for a reason, so I will explain why that is. So let's go ahead and plug these numbers in. What is the square root of 0?
0.
Good. What? You got it, they are perfect squares. What is the square root of 1?
1.
Square root of 4?
2.
And the square root of 3?
3.
I'm sorry, square root of 9 is 3. I'll never get over doing that. Okay, so we got 0, 0, we got 1, 1, we've got 4, 2, and we've got 9, 3. We're going to graph them, we connect them, and as you can see, it looks like the one that we had on the previous page.
I don't know, Ms. Russell, that line's a little, I don't think it really is.
That's true. My drawing is, inferior, but it's the same idea. So, is this graph increasing or decreasing?
Increasing.
Good. And it's increasing from 0 to positive infinity, right? Why isn't it increasing from negative infinity? Very good. It only exists in the first quadrant. Now, there are square root functions that exist in other quadrants, but that's because of shifts, and we'll talk about that in the next slide. So, the domain of this is going to be from 0 to positive infinity, and the range is also going to be 0 to positive infinity. Because as you can see, it starts at 0 and goes up forever. It starts at 0 and goes to the right forever. Okay? End behavior is going to be based on your domain. Now here's something that trips people up a lot. End behavior is looking at the two end points of the graph, where it's going. So in this case, right here, this is looking at this, and this is looking at this right here. So on this end, is anything going off to infinity?
No.
No, it starts at 0, and its f of x ends at 0. So when your graph has a solid point without an arrow going, it's always just going to be the coordinate of what that point is, okay? Now as for the other side, it's going to positive infinity. From positive infinity, it's going up to positive infinity. It's going upward, it's going to the right and up at the same time, okay? So any questions about graphing the square root parent function? Okay, so now we're going to go ahead and try a cube root function. So a square root is a square root because it's the perfect product of two identical numbers, like 4 times 4 is 16, 3 times 3 is 9. Any ideas on what a cube or a perfect cube is? Very good. It's something multiplied together 3 times. Okay? So in that case, maybe it's easier to start with the positive. What is the cube root of 8? 2, because 2 times 2 times 2 is 8. What's the cube root of 1?
1.
Good. The cube root of 0?
0.
Cube root of negative 1?
Question.
Yes.
If you wouldn't 3 times, if 3 times 3 times 0, it's not. Never mind.
Okay. But you're good. You're thinking about it. That's good. So let me explain a little bit about the difference between a square root and a cube root. A square root is an even root, right? Like the 4th root, the 6th root. Even roots cannot take roots of negatives because there's no way to pair up two identical numbers and get a negative as a result, okay? But with a third root, isn't it true that you can multiply 3 numbers together that are negative and it will remain negative? So that's why odd roots are okay to be negative. So what is the cube root of negative 1? -1. What is the cube root of -8? You got it.
But wait, wouldn't it?
Think about it this way. -1 times -1 times -1 is -1. So the same number 3 times multiplied together gives me -1. Does that make sense? A little? Alright, I'm plotting the points. Like so. And all cube root functions are going to have this appearance to them. Okay, whether they're flipped around, whether they're stretched out, it's always going to have this general shape. Okay? Does everyone see what I'm saying by that? It's like a sideways S shape, elongated. Okay. So the cool thing about these is their domain and range is really all real numbers all the time. Okay, that's why cube root functions are nice and easy. And is this one increasing or decreasing? It's actually always increasing. It's just increasing at different rates at different times, right? So it goes slowly up and then it takes a quick up and then it kind of just levels off, but it never actually decreases. So this one actually is increasing throughout its entire lifespan. I know. It just never goes, it's so positive. So end behavior, that's when we're looking at what it's doing at these endpoints, where it's going from here, its trajectory, okay? So as we go off to the negative infinity direction, we not only go to the left, but we also go downward in that direction, right? So this is actually a negative, which I wrote a positive, just ignore that, sorry. And then over here, as it goes to the positive infinity direction, it's also going upward. And that's really typical of a graph that's increasing always. Because on the left, it's of course going down because it's coming up from going down, right? All right.
There are 3 pages to these notes. Oh my gosh.
It's going to be okay. We're going to condense it a little, hopefully, depending on how you guys understand it. So remember how we've talked about vertex form for quadratics? We've talked about vertex form for absolute value functions. Does this look somewhat familiar with the A, H, and K?
Yeah.
So the A, H, and K are the same with a radical function as well. They mean the same thing. So the A indicates if we have a reflection, and that means the A is negative, we have a reflection, over the horizontal line y equals K, K being whatever your K is in your equation, okay? The vertical stretch depends on the absolute value of your A. So if you take the absolute value of your A and the A is greater than 1, that means that you have a vertical stretch. This graph gets it goes up faster. If you take the absolute value of A and it's actually between 0 and 1, so it's like 1/2 or 1/3, that means it's actually a compression, so the graph goes slower. And then of course we have our typical horizontal and vertical shifts, and as we know, horizontal shifts always are backwards from what they look like, so if it's subtraction, it's actually to the right. If it's addition, it's actually to the left. So we'll talk about that. Let's go ahead and analyze number 3. So as we look at number 3, what do you notice? What is the A value here on number 3? Good. The A value is 2. So sometimes I like to write out what each one is. That's fine. You can do that if you want. So do we have any reflection going on? Is my A negated in any way? No. No reflection. But we do have a vertical stretch, right?
Yes.
So the vertical stretch is by a factor of 2, and that's from the A value, okay? That tells us about vertical stretch or compression. Now 2 other things are going on here. We have an H value of technically a -4, right? Mm-hmm. So that means we go horizontally 4 units left. So remember, horizontal is always backwards. If it's positive, it's left. If it's negative, it is right. And then K is as is. So what does this part right here represent, the -2? Good. Vertical shift. Two units down. So what that means is we're taking the graph that we graphed on the previous page, the square root one, the first one. We're now stretching it by 2. We're shifting it 4 units left and then down 2 units. Okay, so that's what the end result is going to be. Now before we describe any of the transformation, the only thing we can identify right now is the vertex. and that's just h comma k. And remember, your h always changes sign. Okay? Now everything else is going to be easier looking at the graph once we've come up with it. So we have this cool way of coming up with the graph using the original graph. So let me talk you through it a little bit on Desmos first, okay? Because that kind of clears it up a little bit. So in the red is the original parent function for a square root function, the first thing we graphed today. In the blue is basically when we take the a value and we do a vertical stretch of 2. That's what happens. It goes up faster. And if we have something in the green, that means that we reflected it as well. But we're not reflecting right now, so we're at this point. But there's 2 extra things we have to do. We also have to shift it 4 units to the left, and we then have to shift it 2 units down. So sometimes it's easier to do this in steps. So instead of doing it all at once, what we're going to do is we're going to actually graph just the vertical stretch portion, okay? So how we're going to do that, the table that we have here represents the original function. If we're doing a vertical stretch, that means that we're multiplying the y values by 2. So in this case, our a is 2. So what we're going to do is we're going to take this column and multiply each of these values by 2. So what is 0 times 2? 1 times 2? 2 times 2? 3 times 2. So now what we did was we just came up with the y values that would make up the vertical stretch of the graph. Now I want to point out to you on Desmos real quick, I'll bring it back, I'm sorry. Notice that none of the x values change with a vertical stretch. It's only the y's that change. They get multiplied by 2. So that's why the x's stay the same, okay? So now, everything I highlighted in the orange, these represent ordered pairs, like 0, 0, 1, 2, and so on. So we're going to go ahead and graph these points, okay? So go ahead and graph 0, 0, and so on. 0, 0, 1, 2, 4, 4, and then I can't go any further. Now keep in mind, this is not the final form of this graph. Now we have to apply our horizontal and vertical shift, remember? So we still haven't applied these yet. So what we're going to do is we're manually going to do this like we did back in geometry days. We're going to go 4 units left, 2 units down with each point. So 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, wait, 1, 2, 3, 4, 1, 2, and 1, 2, 3, 4, 1, 2. I messed something up, didn't I? What did I do? I don't know.
It should be -3, 0, -4, -2, and 0, 2.
Thank you.
Yeah.
One of them I must have went off on. So does everyone understand how we got the one in the blue here? Okay. So you see how we did the transformation in 2 pieces? That's really common when you're doing harder transformations, to do it in 2 pieces. Instead of me trying to do the multiplication and possibly a reflection and then do the horizontal and vertical all at once, that can get really confusing mentally to do all that. Bless you. So we do it in 2 steps.
Whose sneeze was that? It was adorable. Oh, thank you. You must get that a lot, right? Yeah. The cutest sneeze ever. I have the most ugly sneeze. I wish. I would pay money for that. No.
Alright, everyone good with how we got the final function?
Yes.
So now we're going to analyze that final function. Now does this final function have a minimum or a maximum? It only has one. It has a minimum. And the minimum is associated with the vertex, right? So the vertex is either going to be your minimum or your maximum depending on what your graph looks like. So to identify the minimum or maximum, you're going to give me the y-coordinate of your vertex, which is -2. That means that's the lowest the graph ever goes on the y-axis. Okay? Now, is this graph increasing or decreasing? Increasing. What is its x-intercept? Good. What's the y-intercept? Good. 0, 2, but yeah. So the domain is going to be from -4 to positive infinity, right? What's the range going to be? Very good. So now, this graph has array appearance, which means one of my end behaviors is just going to be numbers. So your one end behavior on this side is just going to be the vertex. Okay, because that's what it's doing. As x goes to -4, it stops at -2, the graph. Now over here, my function's going to positive infinity on the other side, and it continues to go up. So as my graph goes to the right, it also goes up. So see how we're going to the right? But we're also actually going upward a little bit here each time. It's hard to see, but the graph is actually on an upward trend. So does anyone have any questions about this? You got a general understanding of it, you know how to put it in Desmos. Because all the quizzes in my class are allowed to use Desmos, so as long as you know how to interpret and understand the graph, that's the most important part. And if you had to, you know, somebody said $1 million, you better graph this, you should know how to do that too. But use Desmos to check your work. So we are going to skip over the second square root one just for time's sake, and we're going to move on to the cubic one. So I will go back at the end, and I will do that problem so you can have the reference if you want to, and I'll just write it down and you can copy it down with me. So cubics are actually a lot easier to graph. You're going to see that here. So with the cubic, first thing we want to do is we want to look at its a value. What do we notice about its a value?
It's negative.
It is. So since it's negative, that means we're going to have a reflection, right? And we're going to have a reflection across y equals whatever your k is. What is my k here? -4. And we can go ahead and actually graph that line in the end to see its reflection over that line. Now, we also know that we have a vertical stretch of what? Whatever the absolute... Very good, 2. So does everyone understand the difference between a vertical stretch and a vertical compression? Stretch is if the value is bigger than 1. Compression is if the absolute value of the value is less than 1.
So you said vertical stretch or vertical shift?
Did I write shift?
Yeah, you wrote shift.
Oops, so sorry.
Sure.
I'm talking about stretches.
Yeah.
My bad. So now we have a vertical shift. We are going to have a vertical shift, though, of what?
-1. Or 1 to the left.
You're right. We are going to go 1 to the left. But we're going to go 4 down as well.
Oh,
All those things are right. It's just, I was just asking it in weird order.
Oh, sorry.
Oh, it's okay. So does everyone understand how, to recap, we're reflecting across the line y equals -4. We're vertically stretched by 2. We're shifting 4 units down and 1 unit left. That makes sense, the summary of all that? Okay. So now what we're going to do is we're going to take the cubic parent function, and we're going to take these values and we're going to multiply them by whatever my a is. What is my a here?
-2.
Good. What's -2 times -2?
16. What? Wait. Oh, okay, wait. JK. Sorry, guys, sorry.
What is -1 times -2? Good. 0, -2, and -4, right?
Can we just talk about how did I get 16?
Listen, when you're doing all sorts of math, look, I was talking about vertical shifts when I was talking about stretches. So these are the new coordinates, okay? We just took them and we did something to them. So I'm going to go ahead and graph the new coordinates. -8, 4. -1, 2. 0, 0. 1, -2. And 8, -4. Now you're going to connect these. It always has this shape, like I said. It's hard to draw freehand on this thing, but you get the idea. Now, the vertex is always the middle point. What is, no, we don't have the vertex yet, 'cause we haven't finished graphing it. What am I saying? That is the vertex of this graph, but we haven't finished graphing our final form yet. What do I need to do with each of these points?
All the transformations we came up with.
Good, we have to do the shifts now, right? So we're gonna go left 1 unit, down 1, 2, 3, 4. Left 1, down 1, 2, 3, 4. 1, 1, 2, 3.
Ms. Wilson,
Yeah.
how do you know which shift to do first, like the vertical or the horizontal?
Good question. It's up to you because it doesn't make a difference. 1, 2, 3, 4. Yeah, it's not like slope or anything because as long as you do both of them, it doesn't matter. So here's our final form. And this puts my vertex at -1, -4. Is that expected?
Yes.
Yeah, we expected that, right? What is my x-intercept?
6. Oh, JK, 9. Oh my gosh. -9.
-9. What is my y-intercept?
6.
Good. -6.
Miss Wilson, I'm done talking today.
Oh, stop. It's fine. At least you're trying. And I see you're understanding. You're just saying stuff slightly off. Is this graph always increasing or always decreasing?
Increasing. You're joking. How is that decreasing? First off, pause.
You always read from left to right. Stop it. You don't hate it.
No, I do.
You love math. Domain and range for any cubic function is always all real numbers unless it's bound, which is a whole other thing. And then end behavior, as x goes to -infinity, because both of these are going to be going off to infinity in one direction or the other. So what's happening on this side of my graph, as my x's get smaller, my y's are actually going upward. And as my x's get bigger, my graph's actually going downward. Make sense? Maybe?
We didn't do the decreasing one.
Oh, we didn't have to do the interval for this one. The line was just to write the word decreasing.
Okay.
If you're wondering what it is, it's just -infinity to +infinity though. Because it's decreasing forever. It's very negative. Okay. So, sometimes, unfortunately, you're going to graph a cubic or a square root function, and it's going to have a really wonky x or y intercept that you can't, like, it's not going to be at a nice point like all the ones we just did. So I'm going to show you how to find them algebraically, need be. But keep in mind Desmo is also a useful tool for this. Just click on it on the graph. But let's talk about it. So x-intercepts always occur when you set the equation equal to 0 and solve for x, and y-intercepts always occur when you plug 0 in for x. So these are like two important lessons in math that apply to all sorts of different mathematical equations. These two concepts apply to every single type of graph you'll ever see. All right, so it's not just these. So what we're going to do is, to find the x-intercept, I guess I'll do this one in blue. You take the equation and you set it equal to 0, okay? And then you're just going to solve it. And then I divide. So 5/2. And then how do I get rid of a square root in math?
You
Square it. Got to square both sides. And that's going to give me x plus 3 is equal to 25/4, which I can put in the calculator, because why not? 25 divided by 4, that's x plus 3 is equal to 6.25. And then what's the last step?
add 3 or subtract the 3.
Subtract the 3.
I'm
X equals 3.25. So that's my x-intercept. Now, how you find the y-intercept is instead of setting equal, you're actually going to plug 0 in for x, okay? So this comes out to be f of 0 is equal to 2 times the square root of 3 minus 5. So this is where your calculator, comes into play here. Square root of 3 times 2 minus 5. That one's approximately going to come out to be negative 1.54. So see how that one wasn't so nice? Yeah, it was rude, honestly. So if we move on to the next one, now we're doing cube root. So there's some important lessons to learn about cube root. If you set this equal to 0, we're going to add 3 to both sides. We divide by the negative 2. We get the cube root of x plus 2 is equal to negative 1.5. And then to get rid of a square root, we square both sides. So what do you think we do to get rid of a cube root? Cube both sides. This gives me x plus 2 is equal to negative 1.5 to the third power. Which is negative 3.375. So I subtract 2, and I get x equals negative 5.375.
Why are you saying that so question marky?
Because it was hard to read on the calculator, and I'm like,
well, you can do that in your head. It's a whole number.
yeah, true. Saying all those numbers, though, just triggers my dyslexia, so I'm always like, am I saying it?
Do you actually have dyslexia?
I don't know, because when I was younger, I would only do it with numbers, which is, I'm literally a math teacher.
That's funny.
So it's ironic, but yeah, you guys will hear me sometimes. I will say the number backwards. Do you guys ever notice that?
Yeah.
Wait, what? Like, do you say F for? Like for 3?
No, like, I will say, like, instead of 74, I will say 47.
Oh, yeah.
Or I will say the answer to, like, I will be like, what is the square root of, and I will say the answer to the question.
Yeah, you said that literally 3 minutes ago.
I do that all the
What's
time.
the square root of 3 and the actual question is supposed to be what's square root of
It's a
7.
struggle.
I thought that's what she was talking about. I was like, Miss Russell, that's the stupidest thing I've ever heard anyone say. Then I realized that I was the one being stupid, so don't worry.
I do that now, and I have ADHD.
I have dyslexia.
Guess we never know what's wrong with me. Definitely something, but we don't know what it is.
I think it's safe to say that.
Safe to say that whatever your issue is, you can still be a math teacher, so it's alright. So I just plugged in 0 for x here. And if you're wondering how to do a cube root in your calculator, it's the same thing as putting it to the 1/3 power. So if your calculator is not that fancy, there is a workaround. Even the dollar store calculators know how to do it.
Wow.
I know. Negative 5.52. Okay. That's what it is. So this is kind of like a lengthy process. Not totally always necessary, but like I said,
It is
Desmos.
quite lengthy.
Desmos is useful. You're welcome to use it anytime you want in here.